Oh, right. And see, because I need to tune. Yes, yeah, I can see it clearly, but just yeah, the earlier position was better. Oh, no. Now it's we are missing the bottom. Oh, yeah, good. Okay, good. But your Zoom is mirrored, so you don't know how to solve that. That's fine because others will watch normal. Really? Yes. Others people see this mirror reflected. I can show you.
Oh yeah, I see normal. How come? I think that's because usually you see yourself, so like you raise your hand, you want to see the mirror image.
I mean,
So it's thinking that's the webcam, even though it's not a webcam.
okay.
What does this leaf mean here in the tree?
My impression is hypothesis. I found it. I was on a hike. I found a tiny plant growing inside of each plant. There's substructure.
I see. So Misha has his reflection of the current status of high energy physics. There's a tree, picture of a tree.
Yes, right. I saw that.
Yeah. He used different color to represent what he thinks is more lively, less lively. Green, of course, means more lively too. But your which one other one?
Sure.
Also there.
You think you will use markers?
This was okay.
Sounds good.
That's enough.
Maybe a good discussion at the end.
Yeah. Yeah. Maybe let's know with others, but let's begin. Today we're very happy to have Ethan Neal from Colorado, University of Colorado at Boulder. He gave an excellent colloquium yesterday about the very exciting updates on the stereo side with the calculation for lattice for G-2. But today he will give us a different topic, talking about our lattice insight for composite new physics. Ethan, please go ahead.
All right. Thank you for the introduction. And thanks again for inviting me. It's so yeah, I'm going to talk about this is going to be another sort of lattice focused talk yesterday. And I'm going to start with some motivation for sort of composites DSM models. I would say my primary target audience for this talk is those of you who are interested in phenomenology, which is sort of a guide to using adapting more lattice results for phenomenology of these kinds of strongly coupled models. But I think just generally, if you're interested in strongly coupled physics, I'll have interesting things to say. So after the motivation, I'll make some general remarks on how lattice results should be used as phenomenological models, because a little bit of a language barrier. I find in the way that people describe things, if you're doing pen and paper Pheno or if you're doing a lattice calculation. And then I'll go over several lattice results. I organize things sort of by type of state, so pseudoscalar mesons, vector mesons, baryons, and then scalar mesons. All the results shown are going to be from a paper I wrote with Tom DeGrand, our complex number given there, unless I note otherwise. Okay. So for motivation, there are many proposals for models of new physics that include strongly coupled interactions. I have in mind particularly the kind of strongly coupled interactions that we are familiar with in the standard model, Yang-Mills interaction like QCD. And if you have this strongly coupled interaction, you can find that you naturally have composite states. So this can come in many interesting forms. Composite Higgs models have some new strong interacting Higgs theory beyond the electroweak scale. And then the Higgs is a composite bound state, that interaction. The other parts of the electroweak sector tend to have compositeness as well, including the top quark in some models, but not all of them. Composite dark matter is another sort of broad class of models where this kind of physics shows up. You can have a dark hidden sector that could be and composite Higgs. This is a feature of things like neutral naturalness model, creating a mirror copy of the standard model. That's another SU3 QCD. This can give rise to dark matter as a composite state. It's kind of a nice and natural thing from a dark matter point of view, because you can have coupling to the standard model, the relic density in the early universe, but the dark matter we see today can be a sort of strongly bound together state of these things, which doesn't interact very strongly with us, and so it's not ruled out by direct protection. There's other kinds of interesting models, composite axioms, composite right-hand neutrinos, things like that. There's this sort of landscape of interesting, you can do where strongly coupled physics is underlying it, and the appearance of strong coupling prevents you from understanding everything using perturbation theory. So lattice calculations can help to fill in the blanks because it's a non-preservative technique that can get us information. Yeah. So as sort of a general comment, there's a big and kind of rich space of strongly coupled theories out there. So here's a phase diagram I like to show. This is just a phase diagram that has QCD as one point. These are SU-N gauge theories. I take some amount of fermions called NF. I put them all in the fundamental representation. I just draw this phase diagram, and this is what we know the phase diagram looks like. If QCD is 3, NC is 3, NF is 2. On this plot, I'm just counting the light or lights and the massless degrees of freedom. And if you take just the large NC limit from QCD, that's the top limit, nothing very much happens. Why large NC is a good, actually gives some reasonable description of QCD itself. You go in the other direction, you see this kind of interesting phase structure showing up. There's a phase transition, an infrared conformal phase, before you get to the point where you lose asymptotic freedom. This is blacked out on my plot because you want to do lattice calculations, you need that asymptotic freedom to be able to define a continuum limit. But I'm not going to go too deep into this sort of phase structure in this talk or into the sort of conformal phase transition. That is another active area of research for lattice gauge theorists. It's an interesting question as to exactly where the boundary is and what the nature of the transition is, what's the order, and so on. But I'm showing this more as sort of general motivation, that there's this big basis from a couple of theories. Some of them are very similar to QCD, some of them can be very different. And the other point I want to make is, when you do lattice calculations are relatively, they take a fair amount of time to do. We like to study one particular theory. So, whereas if you're doing phenomenology, you often have in mind some broad class of theories, and you can learn something about the broader class of theories just by doing studies of individual theories.
So sorry, the asymptotic. So you need that, you said, because in the UV, the coupling will become strong, and then you won't be able to have a continuum limit. That's what you said.
Yeah, exactly. That's one of the things lattice usually relies upon, is that as you reduce your lattice spacing, the coupling is becoming weak at the scale of the lattice spacing. So the theory is becoming perturbative. You can sort of match on to the free limit. If you lose asymptotic freedom, then you can't do that.
And there's no other way around that. So.
Well, so there's speculation that at least for some of the theories that exist up there, there might be another ultraviolet fixed point that would be interacting. So it would be sort of an asymptotically safe scenario. in principle, you could define a continuum limit for the theory at that interacting fixed point, but it's much more difficult, right? You don't have perturbation theory as a guide. So there are people who are playing with that and trying to study it, but I think that's very difficult.
Sorry, just to follow that question.
Yeah.
In your lattice calculation, of course, you truncate your numerical study at the lattice spacing, which is high scale. All you need to do to assume is beyond that scale, there's no drastic contributions to the the correlation functions you are trying to calculate.
Mhm.
So it's essentially about whether there are another huge contribution when I take the continuum limit or not, right? So if I assume there's no big distortions to the low energy correlations I care about, the lattice calculation will still be fine. In that sense, the asymptotic freedom loss is not forbids me from saying my lattice calculation at the finite lattice spacing is still meaning. I would naively assume that.
That is true. I believe that is true, but you still have to have a well-defined continuum limit. Like, I want to say, if there's no ultraviolet fixed point, if the theory just sort of has a Landau pole in the ultraviolet limit in the coupling or something like that, it's not clear that you can sort of. It's not clear there is a regime where you can just take the lattice spacing shorter and shorter and things will not round. Right, that's the problem. Okay. So yeah, so the main takeaway for this plot is not actually the vertical axis, it's more the horizontal axis. Is that if you are interested in doing this phenomenology with the theory, which is sort of QCD-like, there's the sort of large fraction of the space where there's no phase change. Everything stays relatively QCD-like, and you can try to understand things in terms of large n limits like this. Yeah. Which leads to that question, which is if you're doing model building and you want to use something like the large n expander, you have that as a tool while you need lattice gauge theory. What's the point of this talk? So lattice can give you extra quantitative information, not in the large NC expansion, or it's difficult to get. I can do a few different things, right? We only have one real world example of a theory in this space, which is QCD, which we know a lot about, but we shouldn't assume everything generalizes from that. If we use lattice, we can test things like the large N expansion. We can validate it. We can see that it actually works. There are a lot of studies that have done that explicitly. We can search for things happening that are different from QCD, some emergence of phenomena that might require new models, and I'll try to show you a couple of examples of where I think that is being seen from lattice simulations in the talk. And we can fill in details that the models don't provide, right? So if you do large NC expansion, it's very easy to sort of figure out what the scaling with NC is of certain matrix elements, observables, but you still need to know the prefactors, the coefficients, right? So this is sort of like you're doing quantum mechanics. Symmetry gives you a huge part of the story, but not everything. You still have to calculate coefficients of the symmetry, things you can do by symmetry, the reduced matrix elements, if you want to actually make a prediction. Okay. And that's something lattice can give you access to. You can compute, say, the spectrum of baryons as a function of NC, and you can take off like numerically what are the coefficients in order, not just the scale. Okay. Now the other argument you can make about strong physics, if you want to do phenomenology, is that you could just take a bottom-up approach, right? We haven't seen new physics yet. When we see if we're likely to sort of just see the edge of it, if we just identify the right effective theory, we can make statements about wider physics, dark matter detection. Just using that, we don't really need the extra input from lattice, which is sort of coming at a higher UV scale, not with the UV. I think this is great. This is a useful approach, but it has some limits to it, right? So first of all, the EFT has less power than the underlying theory, right? If you write down a chiral perturbation theory for QCD, there's some number of unknown coefficients in the EFT. And in fact, if you go to higher and higher order, there's more and more unknown coefficients. Right? In principle, it is a number of orders of constants in chiral Lagrangian, but they're all fixed by handful of actual coupling in QCD, right? If I know the up and down Quark masses, range mass, just with the energy scale of QCD, that sort of all of the energy constants in the chiral. If you know the underlying theory has a handful of parameters if it's strongly coupled compared to the effective. You can infer constraints, things like that. There are also things there are also interesting physics questions that are not accessible easily to the EFT. It comes with this energy cutoff. So if you're really sort of at the threshold of the collider discovery, the EFT is probably fine. You want to ask questions about gravitational wave production from finite temperature transitions, which is most people are interested in, putting this strongly coupled dark matter models. That's much more easily done with something like lattice models. All right. Your name, the motivation.
Can you go back to the last slide?
Sure,
Just
sure.
about the last line, the EFT plus lattice. What's the advantage there? You're arguing EFT is lack of predictive power, right? I need the lattice from UV theory to match the coefficient properly.
Right.
What does this hybrid bring?
It's right. It sort of fills in things that you miss if you only look at EFT. There are correlations between the coefficients, if there are constraints on what their values would be in terms of the underlying parameters of UV theory. I will show examples of this later of how this works. That there are existing strongly coupled models. You write down EFT, you make some plot, some big plot of like what the collider constraints look like, and then you turn on lattice simulations and look at how these parameters vary, and you see there's only a narrow slice of the plot that really should be worth considering.
Yeah, so it doesn't reveal the whole UV connections to the IR, but maybe allow me to know partially some constraints. That's
Right.
Yeah.
I mean, this does come with a caveat, I could say, that there are many UV theories. I started with this plot of this big theory space that you have two parameters in. So to some extent, you have to. It's only really useful when there are trends in this space, when there are statements that are true across many UV theories. But yeah, I think this will be clear when I get it. Okay. So I'm going to give a couple different examples. Again, the theory space is kind of large. My starting point is going to be specifically SU3 fundamental representation. So just QCD basically, and then looking at how things changes and vary the Quark Mass. So there's many well-motivated VSM models where this is either required if you're doing like a mirror sector, like SU3, QCD is the only choice, or at least a viable choice. And the nice thing about this is that there's this enormous literature, basically as an accident, a history of what QCD behaves like with heavy quarks. Early lattice QCD studies basically did these calculations because they were numerically easier than doing it with physical quarks. And there's a wealth of knowledge out there to have to be reinterpreted for use in DSM model. So this is again the main paper I'm drawing results from. This paper I wrote with Tom DeGrand, where we collected a bunch of these older SU3 lattice results together at unphysically heavy quark masses in a way which is hopefully useful for phenomenology. Okay. So before I get to showing those results, I have a more specific comments about how to use lattice results for composite phenomenology. Again, this is sort of some points of confusion that I want to dispel, but that sometimes come up in translating from lattice results to, So one thing to keep in mind, important point is that perturbation theory is sold separately. It's not included in the lattice simulated. If you use QCD lattice results, or say heavy flavor decays, you know this intimately, right? So for example, the decay rate of a D meson, a term meson, the lepton decay rate, I can write using this formula here. And this separates a few things. There's a kinematic factor at the end, there'll be electroweak dependence in the middle. So I have the D Fermi squared, I have the CPM matrix elements. And then at the beginning, I have the QCD function. So the strongly coupled physics only enters through the mass of the D meson, which shows up in the kinematics, and then this quantity FD, which is the decay constant, and that's just a matrix element. So I'm showing in red here, QCD matrix element. That's what defines FD, is just the overlap with the D meson with the quark current that then couples to the electroweak. And the key sort of physics idea here is that you have factorization, is that you can do this separation. You can separate strongly coupled matrix element from all the perturbative coupling, all the kinematics, and you get the right answer. You can treat them separately. And this is really good news for people who do lattice QCD, because it means you don't have to include everything. You just isolate the strong dynamics. If you want to study, say, electroweak physics, you don't need to include the electroweak scale within your box, which you really can't using modern state-of-the-art computing. There's just not room to fit QCD scale and the electroweak scale. But you don't need to. This is also good news if you're doing model building, because if you're interested in making some change to the theory, you want to study some analog of this in a different theory with a different version of the electroweak couplings, basically. You can just make those changes and you plug in the same strong coupling matrix elements. Yeah. You can do this separation reliably. Okay. We talk about dimensionless ratios. So
sorry, can you go back just to make sure? This separation of QCD and electroweak physics, is that a guaranteed thing, or just our approximation? For instance, if I care about the electric correction to this process, right, the next in order correction. So of course I can do this calculation, assuming D overlap with D mass and D overlap with the quarks, and I calculate the correction perturbatively. Then there's also a possibility for the D mass and have wave function overlap with the two quarks plus one photon, and I need to attach the photon and close the loop in some sense during that calculation. We are dropping those terms by is that assumption or yeah, this factor? I'm asking the nature of this factorization.
Good. I think factorization is not itself an assumption, but I think if you want to do higher order corrections, you may potentially need more QCD matrix elements. So I think in that example, potentially, if you're considering photon emission internally from the D meson, you might need an additional matrix element which have a overlap with the D with not just the electroweak current, but with a photon current.
Yeah. So in principle, I need to include more the QCD matrix element. If
yeah.
So
but the idea of factorization is I can still, if I want to do loop order calculations in my composite dark matter model or whatever I'm working with, I may need additional matrix elements to do the calculation, but I don't. Factorization is still there, right? I just need those strong coupling matrix elements. Okay. Let me talk about dimensions just briefly. This is another common point of confusion. Okay, so lattice calculations, they're numerical. The computer only works with numbers. That means everything is dimensionless. You have to put in your dimensions by hand. In particular, you have to set your energy scales using some physical quantity that you decide on. And if I ignore the Quark mass for a moment, of course, QCD, I don't like to do this once. It's a one parameter theory, right? There's a dimensional transmutation scale, like QCD or something like that. And that fixes the coupling measured at some momentum scale, basically. That's the only parameter I need to fix. And if you're doing phenomenology, you might write down something like lambda QCD and say that's the scale of the theory. Problem is there's no such thing as lambda QCD. It's not a physical scale. So if you say lambda QCD, you should say what you mean. And in fact, there are different examples of this you'll find in the literature. It could be the nucleon mass, that's a good physical scale, so 1 GeV. It could be for QCD the vector meson mass, that's 700 MeV. Some people use the perturbative lambda parameter, that's well defined. And say on that bar, that's about 400 MeV. That one, the last one is especially bad because it's also not for normalization scheme independent, right? I had to specify MS bar, the other two things are physical. What's convenient will depend on what your model is that you're working with, what the theory is. But the sort of warning is that you should not rely on the existence of a generic sort of scale of the theory. You should always fix into the physical. And so, for example, if I'm doing dark matter theory and some analog with Baryons, my dark matter candidate, that would be a natural way to fix the scale in that model. The other thing to keep in mind is that when there are additional dimensional inputs, you have to do a simulation at fixed ratios. So for example, the quark masses cannot be adjusted after the fact. I have to fix the ratio of quark masses to other physical scales in my problem. And so that's part of the point of what I'm going to present today is sort of lattice results obtained at many different values of quark mass. You can sort of interpolate it in space. Quark masses are also bad parameters from the point of view of lattice calculation. They're not a normalization group invariant. I'll come back to that in a moment. But fermion masses are just a bad parameter to use. You should again use something physical like a hadron. All right, so this is a little more technical. This is sort of some common symbols you'll see in lattice papers that are used to set scale that have nothing to do with which are physical but are not sort of familiar real world examples. So good to review what they are. So one common set you'll see are called R0 and R1. These are the so-called Zomer parameters. These are determined from the quark static potential. So you present a quark anti-quark pair, you measure the potential as a function of the distance between the two, and then you define the values of the parameters from the derivative times R squared being equal to C. So it's sort of you're trying to find roughly where it's turning. It's some parameterization where the potential turns over for Coulomb-like thing. And the two different numbers R0, R1 are different choices of the constants in that equation. The other common scale setting things you'll see are called T and W. So T0, T1 are extra weird because their units are a little strange. The square root of T0 has units of distance instead of T0 itself. W0 is related. These are a little harder to explain exactly what they are, but you should think of them roughly as analogous to the Zomer parameters. They're defined from purely gluonic physics at long distances. So they're sort of analogous to being pulled from the static potential. Yeah. The way they're actually derived involves running a gauge coupling and is sort of complicated, but I think it's physically analogous to this. So these are the current values of these things. They're all sort of order 0.2 to 0.5 times the channel. Yeah.
These all sound somewhat less physical than just hadron masses. So is the reason they're used is they're cheaper to work with?
Yeah, exactly. The reason that these are used in lattice calculations is because they're purely gluonic. Basically, they're cheap to calculate and they're easy to calculate very precisely. So often these are the most precise numbers that come out of a particular lattice simulation. So that's why they're often used to set the scale. I'm not advocating that anyone should use R0 as a parameter in their composite dark matter model. I think you should recognize what these are and you should remove them and set scales using physical hadron masses if you want to do phenomenology. Okay. So yeah, quark masses are not good free parameters, especially if you want to compare to lattice calculations. Very rarely will a lattice calculation actually tell you what a quark mass is. And that's because the quark mass is not RG invariant, right? So in lattice calculations, it's much more common to report ion mass instead of the quark mass. That uses the GMOR relation, right? The sort of three-level chiral perturbation theory that m pi squared is proportional to the quark mass. So the pion mass is a good proxy, good RG invariant proxy for the quark mass. It has a strong leading dependence on it. So on the left, I show we do have results from several lattice simulations of quark mass versus the pion mass. Details for normalization are not important, but just kind of showing that even up to fairly heavy quark masses, you can see very good reproduction of the GMOR, leading GMOR relation. Everything looks very linear, pi squared versus quark mass. So we want to differ between different models. Yeah, sorry.
What the different colors?
Yeah, so the results of different colors and bibbles are just different lattice groups. I should have said that. So now this is a collection of many results from many different groups, all studying S23 at various different quark masses. The point of the results is to show that there's a little bit of spread here Again, these are older lattice results. They tend to be at relatively coarse lattice spacing. There's some systematic errors that are not fully dealt with. That's the spread that you see. But nevertheless, the quality of everything is good. You can sort of see plausibly there's one curve that goes through everything at sort of level. That'll be universal to all kinds of population. Often it's easier to work with something dimensionless instead of fine mass squared in GeV, save you from doing additional conversions. So on the right, I show m pi squared over mv squared. I should say that's the proxy for m pi squared over m rho squared. We call it mvs over mv, just because it's sort of meant to be more general than UCD. Okay. Last thing I want to note is Largian expansion. I'm not going to go into too much detail here. Again, this can be used for some analytic understanding of the space of UCD-like theories, but I'll refer to the scaling a couple of times. I think you could have a whole talk on Largian C expansion and lattice results. Certainly, there's some basic scaling relations that are worth remembering that have been confirmed by a number of lattice simulations. Meson masses are scaled NC to the 0. They're roughly independent of the number of colors. Baryon masses scale as linearly in NC, essentially discounting. You have NC quarks and baryon. And decay constant scale is the square root NC. These been confirmed both with just gluons and with dynamical quarks in some of these references here. Okay. Let me come to some more results now. Again, I'm going to sort of organize things by type of composite state. So here's a reminder of the PCB spectrum. I showed these slides as well. This is also a good sort of showcase for how lattice PCB is well understood and effective, right? You fix a few free parameters. The different colors are just different groups again, different lattice groups, and they all reproduce the rest of the PCB spectrum pretty accurately. Okay, so here's the sort of breaking down things by category. We have our pseudoscalars in orange, ion, the kaons, eta prime. The red circle points to the vectors, the rho meson, and the omega and phi as well. And then the purple ones are nucleons. Okay, so that's the sort of full octet there. So this is including light and strange quarks in states, right? Kaons and things like that. Phi resonance. There's a lot of other stuff in QCD. Of course, this is not the whole spectrum. There's tons of other states in the PDG. I'm not including the sort of mostly relatively wide resonance things like scalars, higher spin states, axial vectors. I will say more about scalars.
So what is the most precisely predicted meson or baryon masses?
Good. This is actually somewhat of an old plot.
Just to get a sense of precision.
Right. So the most precise thing that you can measure typically for lattice QCD are the goldstones, so the pines and the kaons.
Yeah, but when they use, you already use that as to fix your input parameters.
Exactly. So it's not a prediction.
Yeah.
So in this plot, you can see the most precise thing is whatever here is the omega baryon, or the strange baryon. That's sort of, you know, as a rule of thumb, again, I'm summarizing old lattice results that have heavy quark masses. Heavy quark masses work with numerically. So the strictly strange baryon is relatively precise with only those strange quarks. That's something that people now use to set the scale. You can see even in this example, there's one open point here, red point. So that group actually uses the omega baryon to set the UCD physical scale.
But it's not at the level where you can tell the difference between neutron and proton.
There is a lattice calculation of the neutron proton mass difference. There's a long and dedicated calculation, but yes, that is predicted from lattice QCD. That reproduces the real world result. Yeah. Right. It is a positive.
That's 10% accuracy on mass difference.
On the mass difference.
Yeah, it is a result. Okay. Those are the pseudoscalars. right? So things that are pion-like, kaons, pions, etas, these are pseudo-Goldstone bosons. You really don't need lattice to understand most of their properties, right? You can rely on chiral perturbation theory. But again, what lattice can do for you here is actually predict from the UV theory what are the low energy constants, right? So you can make quantitative predictions. Chiral perturbation theory tells you that m pi squared is linear in MQ, but doesn't tell you what the slope is. Lattice can tell you what the slope is. The other thing that lattice can do for us is I'm going to go to much heavier Quark masses than you would probably trust chiral perturbation theory, and show that things are actually pretty regular at the sort of 10% level. Yeah. So here's a couple of dimensionless ratios. So the horizontal axis is m pi squared over m rho squared, basically. We work in a convention, or sorry, in the vertical axis first. Vertical axis is m pi squared over f pi squared. So it's the pion decay constants, the matrix element, pion to vacuum. And we work in a convention. There's different conventions for f pi. We work in the 130 MeV convention. If you're not familiar with the convention, don't worry about it too much, but we have an appendix in the paper. And you can see at intermediate Quark masses, things are sort of very linear. This m pi squared over mv squared, think of this roughly as mq. If you're at sort of intermediate Quark masses, it's approximately mq, because m pi squared goes with mq, and mv doesn't depend that strongly on it. And so you can see in the middle here, things are pretty linear. So I brought through this green curve to guide you on. And there are small variations outside the error bars that sort of indicates underestimated systematic effects. A lot of these things are at finite lattice spacing and not being extrapolated, but nevertheless, we get pretty good agreement at sort of 10% level. What you'll notice is that I'm going right. The other nice thing about m pi squared over m rho squared, which I didn't talk about, is that it can only be between 0 and 1. If I take the infinitely heavy Quark limit of the theory, both the pion and the rho are made of two quarks, and so the ratio of that goes to 1 basically. The opposite limit is like quarks, it goes to 0 if it's pion and massless. So it's sort of nice because I can plot all possible masses in this finite range from 0 to 1. The heavy Quark limit is sort of here in the corner. You can see up to even really heavy Quark masses on this plot. This ratio m over f squared only gets up to about 5 or 6. Yeah, so that's keep that in mind. I'm going to use that on the next plot. So now here's a theory. This is the SIMP dark matter model, which you may or may not be familiar with. The reference up there. So this is the composite dark matter model where the dark matter is dark analogs of the pions. 2 to 3 interactions. This is also a Witten term are especially important, but I won't dwell on that. I'm just drawing on this one plot from their paper. Okay. So this is a plot with m pi on the horizontal axis, and pi over f pi on the vertical axis. And those things can be varied independently, right? I can think of the horizontal axis is setting the scale, and the vertical axis is a function of the Quark mass, which I can change. There's the light Quark mass. So I have 2 free parameters on this plot. To finish explaining the plot, there's 2 sets of curves here. So the solid ones you see going up, that's the value of m pi over f pi needed to get to the relic density. The dark matter model, so you have to live on this curve basically, for this to be 100% of the dark matter. On the right lines, these dashed lines coming down, those are the self-scattering cross sections, calculating chiral perturbation theory. And this line is an upper bound from like galaxy cluster observations, like Boulder cluster. Yeah. You have to live on the solid curve and below this dashed line that sort of indicates standard regions that we want. Yeah. But now I remember the last slide, right? So I have to do some conversions. I have the details down here. Their f pi normalization is a little different. I believe I did this correctly. So the m pi squared over f pi squared from the previous slide should be reduced by 2. So in their conventions, the max value that gets is about 3. Which means the largest this ever gets, up to incredibly heavy Quark masses, where you probably don't even trust perturbation theory anymore, is 2. So the plot should end there. Which means you can't really exist in this intermediate region. So there's a much narrower range of mass values for the pion, where this theory, actually it's worse than that. All right, so you're down here, then your scattering cross section is up here, and it's ruled out by the fourth factor. So this version of the simple dark matter model doesn't have to be viable, render space left at all. And you have no idea unless you look at West.
So did they try to modify the model to make them work again, accommodating more up-to-date?
I haven't fully iterated with them on this yet. I actually in earlier version of this talk, I don't think I did the conversion correctly. I didn't realize it was that constrained, so I just realized this yesterday basically. So I have to talk to them. This is not the only version of the simple dark matter model, right? So this is one. You see, they labeled it like Carlson group. That's the way that Carlson breaking works in PCD. They have other variants that would have other unique equations. So I'm not going to stand here and claim that simple dark matter is ruled out. Sure. I'm just telling you that the real takeaway point is that this plot is too big. Right? If you use the input from the underlying theory, you can't really access everything that you think you can. Okay. We go to vector mesons. So here's some results for vector mesons. Again, in the horizontal, I have my proxy Quark Mass. Here I do a vector and axial vector. And I've overlaid some PDG results, right? So again, all this sort of boxes and X's and things, those are lattice results. The green curves we drew to guide the eye with the linear bits in this intermediate range where everything looks linear. The stars are just from the PDG, converted to our conventions. In axial vectors, I have the A1 and the IC1. So basically, you can read off these are the light quark vector active vector mesons. This range vector meson the phi. These are the charm vector and axial vector mesons. You can see just everything agrees pretty well, but between the lattice groups and with the PDG results, again, it's sort of a thing. The other thing you can see, which you should worry about, is that when you get to really heavy quarks, as you should probably expect, things change, things deviate. And this is effectively the way that I'm plotting things here is kind of inspired at least by chiral perturbation theory, and that's definitely becoming a very bad description of heavy quark masses. So the sort of linear description stops at about 0.7. We see that pretty universally for different kinds of quantities we look at. If you're at really heavy quark masses, then the more natural thing to plot on the horizontal axis is just a heavy quark mass. And if you do that, when you're extrapolating that, you do pretty well again. At the 10% level, none of these simulations were anywhere near the charm mass, but you can just do a simple linear extrapolation. You get it. If you really have only bottom-like quarks or heavier, like only extremely heavy quarks in your quark equivalents in your DSM model, probably you want to use pure data lattice results from analog of heavy quark DFT. So, but I think up to something comparable to charm math, everything, these sort of collected results that we have work pretty well. Okay. That's just the mass. That's relatively simple. We're talking about some of the matrix elements. We're talking about vector meson saturation. So something you can do that was done, has been done in the literature for the early days of trying to understand QCD, is trying to sort of characterize its properties in terms of relationships between different observables. And a lot of this is guided by saturation of the vector channel with a single resonance. You sort of the real resonance is the only thing there. You can get phenomenological models, things like the decay width of the rel. In particular here, I'm writing down two things, the KSR relation there. You can use this to infer things about the rho decay constants. This is the matrix element for this happy. This governs leptonic decays of the rho meson in QCD. Or this matrix element rho to 2 pi, so that's hadronic decay. And these are the predictions. So F rho is root 2 times F pi. The coupling of rho to pi pi is predicted to be again, in terms of M rho and F pi. And then the decay width of the row is predicted in terms of that. And in QCD, these work reasonably well. You can ask the question, what happens if you move away from physical QCD? You change the Quark mass, it would still work. Yeah. Let me come back to that actually. Let me just show you what are the results for the vector decay constants as a function of Quark mass. And it's not very strongly mass dependent. Again, I've sort of put the PDG numbers on here. I think it's a little worse agreement than the mass, but qualitatively, you can see rho omega phi kind of following the curve. And again, heavy quarks, the psi equivalent of the vector decay constant is off the curve and we're bending down. I show the same for the axial vector meson. That's a little bit smaller. But now, of course, this is a direct calculation of this matrix element using lattice methods. You can also take the prediction for F pi, more precise, and try to predict F using KSR. Do that. This is what you get, again, from the same multiple lattice groups. There's a couple weird points like this one where something systematic is happening, probably finite volume correction. But not concerned with that one point. We're concerned with sort of the overall trend. And you can see pretty good agreement actually up to reasonably heavy Quark mass and weak Quark mass. But everything here is in the right ballpark for getting the rho leptonic decay correct.
What is the precision in real QCD that you can get on something like omega or phi decay, whose masses are well defined compared to rho, right? To leptonic branches. Is it in some sense relates to my yesterday's question, right? Is gamma decays by a gamma star, a virtual gamma, right? So it's part of the whole hadronic particle polarization, right?
Yeah,
In a slightly different domain, but
that's true.
but it's if you're telling me that you can calculate vacuum polarization to a better than percent level, you should be able to match that with the leptonic branching tool. So in real QCD, 100%, perhaps.
Off the top of my head, I don't know what the state of the art is for the leptonic rho decay constant. The complication is, of course, that the rho is not really stable, and these sort of at heavy Quark mass, the rho is stable because rho is too high.
Yeah, rho is too wide. That's why I was wondering about omega and phi, whose masses are
Okay.
well,
So right.
well defined, right?
The leptonic decay constants for heavy mesons for things like D decays, those are suffer accuracy from last year's. So yes, you can do those at comparable precision to what we're doing for HPP. These are some of the most precise things you can calculate. And if you're kind of helped by the fact that this isn't the simplest matrix element you can calculate. Decays like rho to 2 pi have been studied. I'll show you some results actually. The other thing you can ask about is the second thing is the rho to pi decay. This is much more difficult to do on the lattice, but there have been direct calculations of the strong decay matrix element. Again, at different Quark masses. So we've gathered those together here. These are harder calculations, and these are more recent from different lattice groups. Why you see some different colors. And I'm plotting this against, so the right is direct calculation of this matrix element for the pi. On the left, this is the estimate using this second KSR relation, so this is basically time decay constant romance. And you can see it doesn't get things exactly right. But they both agree pretty well qualitatively with each other and with degree of dimensionalization of the PDG value that comes from the width of the row. We're interpreting it as this G rho 5 pi. Very little Quark mass dependence. This seems to work. This sort of KSRF vector meson saturation picture seems to work really well. Which is interesting, right? This is sort of proposed for QCD. I don't think there's any particular reason it has to generalize to any arbitrary Quark mass. And even if you change the theories, and now I'll show you some results from something that's not just SU3, you go beyond QCD, there is growing evidence that these KSR relations actually work really well consistently. And there's very little dependence on it. Here's a fairly exotic theory, but I won't say too much about. An SU4 gauge theory with baryons in two different representations, 4 and 6. It's meant to be a composite Higgs model, so that's why it's studied. And you can see basically this is basically the QCD number F, rho over F, or M rho over F rho, rescaled appropriately according to large N. You get the same answer, it doesn't really depend on the Quark mass. You can change the number of light fermions from 2 all the way up to 10 in the massless slide. Again, you see little to no dependence on F. You get the same sort of fixed value for this ratio and rho over F1. This is strongly suggesting that the range of allowed values for this rho decay width basically is much narrower than you otherwise guess. Okay, so now let me come back to applications of phenomenology. This is a paper about composite phenomenology colliders. They change conventions, I rescale things. Don't have to worry about it too much. The blue regions are bounds from direct searches or projected bounds from direct searches. Right, so LHC, HLLHC, for future FCC proposals on the right here, 100 TeV, I believe. And there's also indirect bounds shown, the dashed lines show, where you can get from indirect studies of this division study Higgs potential. But again, this is something where I would argue they made the axes too wide, or if you want to sort of use information from the UV theory, you can narrow in on this plot, is a better way to say it. If I take a likely sort of G rho value from the lattice, I was just showing you is very consistent across Quark Mass. I get my orange band here. Sort of 10% share. What's telling you is that this coupling pretty universally for lattice calculations, as you change the parameters, doesn't change that much. It gives you something around this. It's a relatively wide variance, and it doesn't look like something where LHC direct searches are going to give you much information. In fact, I should say there's one line there I didn't mention, the red dash line. That's actually a warning from the authors. The authors say, if you're above this line, the width of this resonance is so wide that our analysis might not even fly. It might be interesting to think more about focus searches for large width objects if you're interested in other Higgs phenomenology like this.
Well, there is one very large width object inside the standard model QCD that you mentioned as a sigma as well, right? I mean,
Yep.
It used to not even exist in the particle data group, but then they sneaked it in. So I guess you should see its presence at some level in the pi channel.
Yeah. And so that's right. The sigma is sort of seen as a very broad pi resonance. It's very difficult to look for. Doing any kind of LHC search for a the equivalent of a rho meson from a composite Higgs model is also going to be much more difficult if it's a very broad resonance, but it's sort of worth considering. And so when you're doing projections like this, worth considering whatever. I mean, maybe if you do, I don't want to say it's difficult, but as you say, the sigma is in the PDG right now, so people's understanding of how to find broad resonances, I think, has improved. The data's improved, so. I think I'm just making the point that it's motivated by the lattice study to think about this. Okay. Let me keep going. Baryons. So the masses again of baryons. So baryons you can sort of classify broadly by spin, the spin state, spin 1/2 versus spin 3/2. Again, I'm overlaying a couple of PDG masses here. The light quark ones. And again, you see broadly what I showed before, the linear fit is becoming, it works pretty well in this intermediate range. If you get to really heavy quark masses, the quark mass dominates the baryon mass and the spin splitting. You can really see that if you go to the very heavy quark limit, you sort of extrapolate and they kind of come together. I think you get to just order 700 MeV. what else can I say about baryons? There's something you get for free, in quotes, from the spectrum. Calculating the baryon mass as a function of Quark mass, you can use the Feynman-Hellman theorem. You may have seen in quantum mechanics class. Just taking the derivative with respect to the Quark mass. If you have the nucleon mass as a function of Quark mass, will you access to the scalar matrix? So it satisfies this relationship. The scalar insertion of the scalar current within a nucleon is related to the slope. And so this is just using those results, numerically taking the derivative, the lattice results, and plotting the inferred scalar matrix element Fs versus the Quark mass. Once again, I can just draw, I see a nice simple linear dependence on the Quark mass. I can draw this curve, and all the results are all nicely on. This is something which is very interesting if you are putting, say, a dark matter model, right? This is the Higgs nucleon coupling. In QCD, this is the sigma term that's discussed in terms of dark matter direct detection. You have a sort of dark baryon model, then you might have a sigma term on both sides for direct detection, and with your target, not the dark matter version of it. In fact, you can use this to sort of constrain how much of the mass in the dark matter model, in a given dark matter model, actually comes from the Higgs mechanism. So that from the coupling and that from the direct detection. So to go quickly on this plot, without dwelling too much on the details here, you can write down this parameter alpha, which goes between 0 and 1. It's 0 if the Yukawa coupling of your dark quarks is 0, and it's 1 if all their mass comes from the Higgs mechanism. Yeah. And in this dark matter model, SU4 dark matter model, this curve is alpha equals 0.64. This is an old Lux 2014 bound, so there's even better direct detection bounds now. But even from this sort of old plot, you can see alpha even around a half is ruled out completely by direct detection. The only way to obtain is with a really light baryon mass, which suppresses the signal, but then you run into another bound sort of on the distance of charged particles in this particular model. So in this class of dark matter models, I don't say too much about because of time, but I can come back if people are interested. You can use effectively these results. What is the scalar matrix element? To say that you cannot generate all the dark mass from the Higgs mechanism. And this is another case where I can take results actually from other theories, and things are very incredibly consistent. So what I was showing you was just SU3 as a function of the Quark mass. Here's more lattice calculations for SU5, SU7, SU4 with the quarks in a different representation. Everything sort of falls roughly on the same curve. Yeah. I don't have a good understanding for why this is. I'd be interested if anyone can come up with one. But there's this sort of very general observation that this scalar matrix element does not depend much on the details of the default in the universe. Always different theories. Okay, the last thing I want to talk about is scalar mesons. Yeah, so in QCD, there is a scalar meson that's a very broad. F0600 is a very broad 2-pion resonance. The pion is much lighter because the pion is a Goldstone boson, basically. But people have seen something interesting happening in lattice studies, which is that, and this is in 2 different theories. So again, now I'm approaching that sort of conformal transition, conformal window transition. I'm just in theories that have a lot of fermion content. So the left plot is for 8 degenerate light flavors. The right plot is for 2 degenerate light flavors in the larger gauge representation, the sextet representation. And these are just spectrum calculations. But I'm just going to highlight two states that I've already circled here. The pions, which are here, are always the most sort of precisely calculated thing. That's the pion mass in black on both plots. And then this thing labeled sigma, that's the scalar meson mass. And you can see in both cases, it's basically degenerate pion, or even a little lighter. This is an interesting state, right? It has the same quantum as the Higgs boson, with the scalar parity positive state. This has been speculated as it appears when you get near this sort of infrared conformal transition, that this is some kind of pseudo-dilettante state. And there's more lattice results coming in that sort of have confirmed the presence of the state, improve the precision, and are trying to sort of get more information on them. So these are difficult theories to study, but more results will be appearing. So it's an updated spectrum plot from one of my collaborations. Again, showing that things are still, the state is roughly degenerate with ion. On the right is a study of scattering, the I equals 2 pi pi scattering, phase shift. This is a useful probe of the low energy effective theory, although this band is compatible with the dilettante effective field theory, but it's also compatible with it's supposed to be Carl theory. Good. I think I don't want to make any detailed points regarding plots on here, which are not even very visible. The point I want to make with this plot is with this slide is just that this sort of interesting light scalar state has been cited. There have been proposals in the literature for effective theories that would incorporate this new light scalar degree of freedom, something like the dilettante. There's been an alternative proposal for something called a generalized linear sigma model, which incorporates it in a different way. And in principle, you can use additional information from lattice to try to distinguish these things. So this is a case where, this is sort of an unexpected or somewhat unexpected thing to emerge from lattice simulations. This is a case where the EFT, if you tried to use an effective field theory to describe these theories that only had ions, you would be wrong. The lattice is telling you qualitatively something's wrong with the effective theory. You have to figure out how to incorporate this new light scalar state, even if you're only working at low energy. And this is a sort of ongoing work in progress to both get new lattice results that can constrain things and to develop what the EFT description should look like.
So this is some spontaneous breaking of the scale again, conformal again. Are these theories conformal or approximately conformal?
Yeah, so these theories are not actually conformal. That's a very complicated story that we should talk about afterwards, probably to get into the full details. But these are not theories that are conformal, but they're speculated to be kind of close to where a transition to infinite functionality would happen. It's tricky to think about because the parameter you're varying to go through the phase transition is discrete, is the number of flavors, right? So it's sort of changing by discrete jumps. It makes it hard to characterize the transition. In this model, this dilettante EFT model, they take the large NC limit, so that NF over NC is a continuous parameter, and then you can sort of think about as you vary that parameter close to where this critical transition happens, then yes, this is approximately a pseudo-Wilson boson associated with spontaneous scales of the group. So that's one construction, right? So that may or may not be the right answer. That sort of requires further numerical tests to actually see if that's the right description.
But what else could it be? I mean, you've got a light scalar particle. There's got to be a reason. Are there other interpretations?
There are different variations on the details, I would say. There are other formulations where you can write down. You write down, say, an arbitrary potential for the dilettante, and you get a somewhat different effective field theory. I'd say, for the most part, that's how people want to interpret it. This is a model that has no dilettante-like interpretation, just sort of added and creates a generalization of a linear sigma model. It's not a very satisfying model. We doesn't have a good explanation as to why it's light. It's just sort of.
In terms of why it's light, that would be the best idea. Right?
I think so. Yeah. Okay. So I'm a couple minutes over. I think so. Let me just conclude. I've motivated this idea that lattice can do a lot for you if you were interested in composite physics beyond the standard model. It can give you constraints on how EFT parameters are related to each other. Help you make things more predictive. Even tell you if there's some interesting EFT feature of the EFT that you're missing, like this light scalar. If you're doing anything that's SU3, there's this enormous wealth of lattice results already out there that you can use at the 10% level. You can ignore details in like systematic error analysis and things like that, which I've convinced you with the regularities that I've shown. You should avoid simulations that are quote unquote quenched. don't include the fermions at all dynamically, but those results are standard. They're much older than most of the ones that I've showed you. I didn't talk about exotic states. There are other things you can calculate within QCD, like blue ball masses. You can look at higher spin mesons. You can calculate a matrix element for something like a gluino or fermion in a higher representation. There are a few results, but just in the interest of time and because those are very specific, I didn't include them. They're in the paper. You can also do things with nuclei at heavy ion mass. There's some lattice results there, but those are kind of controversial. So I'll give you a reference for the controversy, but I would just be aware of that if you're interested in nuclear physics. Yeah, there's sort of a small lattice community interested in this kind of thing, but we're active. We're always happy to talk to phenomenologists and interesting to learn more about what the interesting questions are. So we'll stop there. Thanks very much.
Any further questions?
Yeah, so just a general question, what's the prediction for like getting more accurate results? Is there any limitation? Because you're quoting everything at the 10% level. Can you envision a day when we get to the 1% level with lattice or not?
Well, right. So for certain things, right, if I go back to, I'll pick some example. You're really interested in the leptide decay of a real like psi meson or something like that. Those are available at some percent accuracy, right? But most of these sort of modern lattice calculations are focused on physical real world QCD, understandably. What's not available generally is this bigger picture, just like function of the Quark Mass. That's sort of only concerned at the 10% level. I would say it would be most of the simulation results I'm showing are at least 10 years old. Computing power increases exponentially. It would probably be pretty easy for a modern lattice group to revisit some of these things and improve the accuracy. But I mean, there would have to be a case where you really want better than 10% accuracy, right? A lot of these things we're talking about speculative BSM physics, nothing's been found yet. There's not really going to be a big difference in how you think about things between 10% and 1% accuracy for most of the things I showed.
But even for QCD, people are interested in knowing masses per 1%.
No, so for QCD, people are very interested in knowing masses, but they only want them at the physical points, right? So what you don't get is the whole plot, is the linear dependence at 1%. You only get you get the specific answers for QCD, but not the entire picture. Yeah.
This might be slightly out of left field, but I remember there was some controversy over the last few years about the behavior of adjoint QCD with two flavors, about whether it's in the conformal window or not. You happen to know if that's been resolved, if people come to a consensus?
It depends on how many adjoint flavors you
So
have.
two Mayrons.
Yeah, there's some. I want to say there's been a couple new papers in the last couple of years that I think. Majorana, one direct. There's been a couple more recent works. I think they didn't have a definitive conclusion, but things looked like they were probably formal. I think I can probably find references for you afterwards.
I can also dig around myself. Yeah, I was just curious if you had some.
There's been further, my understanding is there's been some further work, but there's still not a definitive answer for one. For two Majorana. For more Majorana is well known that's sort of a definitely conformal and is a fairly weakly coupled theory.
Other questions? I have a very naive conceptual puzzle here as well. So somehow in my mind that we are trying to use a lattice calculation to feed the measured data, like QCD data, right? So this feeding procedure involves operator insertion. Like what's the wave function overlap between the mesons to different structure of the parts. So does that mean in this such a feeding procedure is essentially a very effective field theory description? I'm just trying to find. I'm really doing lattice plus EFT, and the result, accuracy of my results, and what I'll find to really highly depend on how many operators I put in this point.
Right, so some matrix elements, this is something that I think. Okay, so for people who do say high precision calculations of electric decay in the standard model, the big difficult lattice calculation, people are doing this to, with an accuracy approaching percent level for some things or below. If you're only interested in the electric decay, there's only one matrix element or one or two, you have to calculate all the times. But if you have a sort of arbitrary BSM theory, you can have insertions of different currents, right? So again, factorization helps. You can calculate what would happen if you had a sort of exotic decay from some new physics of like a heavy flavored meson. You just need the additional matrix elements that are not relevant to the standard model. I think for the most part, lattice QCD people who need high precision flavor things have gotten better about anticipating this need and calculating, because the extra matrix elements, the extra sort of different Dirac structures you get essentially for free at the end of the calculation. It's very easy to do that. Visualization can be all the work you do before. But most groups that do that are getting better about reporting not just the standard model matrix elements, but all of the ones relevant for any possible decay. That's the answer your question. I think in general you need more matrix elements than are relevant for a standard model.
Yeah, actually, I'm asking not from the BSM point of view, or slightly not that BSM. So how about the lattice calculation for tetraquark, pentaquark? Okay, of course I have, in principle, I have to insert an operator where the tetraquark overlaps with 4 quarks in my fitting, but my low energy data not necessarily give me input for such kind of operators, at least no complete information on such operators.
Yeah, and there have been studies of that kind of thing. So you can use basically different kinds of interpolating operators. When you get to states like quarks and pentaquarks, it's not clear whether the right interpolating operator to write down is 4 quarks. It's a kind of molecule of meson operators. It's some combination of the two. From the point of view of the lattice, it doesn't exactly. You can sort of answer the question. So the way that people do this is you do a variational calculation, right? You don't just pick one interpolating operator, you put all of them in, and you look at the correlation between all of them, you produce a correlation matrix, and you can answer the question sort of a posteriori, how much of this state is this interpolating operator, or this one, how much of it is 4 quarks or molecules, like that. This is really hard for tetraquarks and pentaquarks, but you can do this. This has been done for sort of simpler states. And that's sort of philosophically how you would approach it. The results do not depend on the interpolating operator.
Yeah. If no more questions, let's thank the speaker again. And even I will be thanks. Thank you. Our faculty community is always happy to have you. How are you? Thank you.